this is going to be homework for part C, in which we have our constantly stirred tank reactor, which is perfectly stirred, meaning our concentration in the tank will be the same as what's going out, which will be important later. And what we're going to need to do is find the differential equations for the changing concentration in the tank and the changing temperature of the tank. And so let's get that done. So it's important to know that this height won't be changing, meaning our volume, our height, and our flow rates will all be constants. So we'll start off by representing the amount of A in our tank as, or not representing, but the change in A in our tank as the change in our concentration times our volume, dt, which will be equal to our flow rate times our concentration of A coming in minus our flow rate times our concentration of A in the tank. And one more thing that will affect the amount of A in the tank is the reaction that will constantly be taking place. And this reaction will be represented by our volume times our reaction constant, K, times the concentration of A in the tank. And from here, since we know our volume is constant, we can take it out front and divide by V, getting us Q times CAN minus Q times CA of the tank over V minus our reaction constant times C will be our change in the concentration of A in the tank. And now we'll move on to finding our temperature, and we can kind of start off by having this cap stuck. But kind of think of it as our mc delta T as our equation for our energy, and we'll kind of go our change in energy, our mass, which can be our volume times the density, times C times T. The change of that will be equal to the flow rate of the density coming in, which accounts for our volume and our density, times C times the initial temperature minus the final temperature will get us the change in energy of the tank as the liquid flows through it. And the next thing we'll need to do is account for the reaction taking place. So the energy from this will be represented by our heater reaction, which in this case is exothermic, so it'll be negative, so delta HR. And this reaction, or the heater reaction, will be happening at a rate of the reaction, which we did solve for up here. So times VKCA. And lastly, the next thing that will affect our energy is our heat transfer from the liquid to the cooling jacket, which can be represented as our heat transfer coefficient, or UA, times our temperature minus our TC, which will get us the amount of energy that's transferred. So that will also be needed to account for when we try to calculate the change in temperature. So minus UA T minus TC. How to do that? And now, since we know our volume, density, and our C will be constant, we can take these out front and divide by them. So we'll end up with our change in temperature can be represented by our Q will stay, our density and C will be out, so Q times Ti minus T over V, which doesn't cancel out, plus our heater reaction times the rate of that reaction divided by, and this V will cancel out, so divided by rho C, And lastly, minus our heat transfer coefficient times the change in that heat from the jacket to the liquid. And that will be divided by everything since nothing cancels out. So V rho C. And that's how we get our differential equations for the change in concentration and the change in temperature of our constantly stirred tank reactor. All right. Okay, for homework 4, part C2, we're going to be numerically solving for the values TC is equal to 290 and TC is equal to 305 using the differential equations we derived earlier. And after we do that, I'll explain the oscillatory behavior once we see what's going on there. So to start off, we have our importing numpy, our SciPy integrate solve by VP, and our subplots. And then we have all of our givens in the problem. So our initial flow rate, our initial concentration coming in, our initial temperature, the volume of our constantly stirred tank reactor, our rho, the density, our C, the negative HR, or heat of reaction, and it's negative to make it fit in a little bit easier with our equation to make it simpler. Our ER, that will go into finding our KCA, our initial concentration, or not our initial concentration, our initial reaction constant, our UA, which is our heat transfer coefficient, our initial concentration, our initial temperature again, and we have our TC for the first one, so TCA, and our second TC, so TCB, and then we'll be running this for about 10 minutes. So to start off, we'll find our function here, CSTR as a function of time, V, and V will have to be unpacked into our concentration of A and our temperature, which will be equal to V. And to get our our KCA, we'll need our concentration times our initial reaction constant. And this will be multiplied by our exponential function of our negative ER divided by our temperature. And then to get our change in concentration, or that DCA, that would be Q times our concentration coming in minus our concentration of the tank because it's well mixed, perfectly stirred. And this will be divided by our volume because that was divided across by initially. And this is minus our KCA, which usually had a V, but that was divided across by, canceling out the V. So there's our change in concentration. To get our change in temperature, it's a little bit more complicated, but we have our Q, it's the equation we derived earlier, times our Ti minus RT, and that will be divided by, it was initially Q, C, and rho, so this would be divided by our volume, and then plus, since our heat of reaction is already been changed to negative, we can just keep it how it is. So our negative heat of reaction times our KCA again, which was divided by volume in this instance. So this would be divided by our C times our rho. And then lastly, we will have our heat transfer coefficient, or UA, times our T minus TC. And this will be divided by everything since nothing in this situation would cancel out. So our rho times C times V, which are all constants, and that should give us our dt. So now we just need to return what we have. So we had CA first, so we'll dCA T, make sure that works. And this needs to be our TCA, or 290, and then we will move on. We'll have the same thing, and we'll call this our TCR2, and the only thing that needs to change here is this needs to be our TCB. Do that. So our results are equal to solve IVP of our function, so CSTR, our time constraint, so 0 to our t end, which in this case is 10, our initial values of the problem, which we have CA first and T second, so CA0, T0, make sure that's right, capital T. We want our dense output equal to true, and our method will be rad u, so it is more accurate. Make sure that what is wrong there? Oh, this doesn't need to be there. Dense output equals true. What's wrong with that? Oh, this was misplaced. Okay, there's that. And now we need the second one for our other temperature, so we'll just call this res2. This is for CSTR2, and then that should be fine. Next, we need to get, I guess, our plot, so our t-plot will be equal to np dot linspace 0 to t end, and we want 1,000 different points. And then our CA and our T will be equal to our res dot solve for every value of t plot, and then our CA2 and our T2 will be equal to our res 2 dot solve of our t plot again. At this point, I'm gonna make sure if we just go from the top, everything still works. All right, and now we can move on to plotting these out. So I figure is make subplots, and we'll have 2 rows and 2 columns. Big dot add scatter. Our x will be equal to t plot. Our y will be equal to c. We'll do CA first. The name of this is CA. I guess we can call it CA1. And the mode is lines. That should be all we need for that. Oh, no, we need our row equals 1, column equals 1. Okay. Then we'll take this, and we'll need 4 of them. This one will be our T1, we'll call this T1, lines, row, column 2. This one will be our CA2, we'll call this CA2, modes, lines, row 2, column 1. And this one will be our T2, so T2, and we'll call it T2. And this needs to be row 2, column 2. We'll just see if this makes what we're looking for. Looks about right, so we can just so as you can see, our initial temperature for both is at 350, and for the temperature at 290, our reactor comes to a steady state with the concentration around 0.95, and our temperature becomes steady as well, and that's fairly boring. But for our 305, you can see it's an oscillatory motion here. So as the reaction starts, the temperature shoots up, increasing the rate of the reaction. And sorry, when the reaction starts, the temperature will shoot up, and because the temperature is related to the rate of the reaction, as the temperature goes up, the rate of the reaction will also go up, meaning the concentration will begin to fall as it reacts faster and faster. However, because this reaction is producing the heat, once the concentration equals or gets down this close to 0, that reaction will begin to go very slow and not produce as much heat, causing the temperature to fall again. And as this temperature falls, the reaction is able, or the concentration is able to build back up. But once the concentration is high enough again, the temperature, sorry, once the temperature, or the concentration is high enough again, the reaction will begin to proceed at a faster rate, making more temperature and decreasing the concentration, and this cycle will continue indefinitely. All right.